All right. Today is the makeup lecture for missing class this morning. That'll be over section 11.8, and it's with regards to Lagrange multipliers. Okay. So before we do Lagrange multipliers, why don't we see via an example why Lagrange multipliers are so wonderful. And the best way to do that is to do a problem without it and then see why it's so valuable so that you can appreciate it when you do have it. Okay, let's do an optimization of volume problem. Okay, let's say we have a box, but it doesn't have a top. So it doesn't have a top lid, okay? Here's the dimensions of our box. Here's an X, here's a Y, and here's a Z. Let's say that the surface area of the box is equal to 12. Whatever, 12 millimeters, 12 centimeters squared, 12 meters squared, who cares? Just 12. So we know that we can add up the total surface area by saying, okay, XZ gives us this thing, and there's one here and one here, so there's two XZs. Then we got XY only, because this XY is the one down here. The top part is missing, so we got an XY. And last but not least, we have two YZs. The YZs are this portion, this side end, and this side end. So we got two YZs. That is what our surface area adds up to. Okay. So then we know that the volume is equal to XYZ, even though we don't know what those values are yet. And okay, what we want to figure out is what is the V max? What is the maximum volume we can attain given a fixed, constrained surface area? Okay, so here's a surface area equation. Notice that this equals to some f of x, y, z, right? So we want to know, given this constraint equation, what is the maximum volume? So this is what we call the constraint. Because we are constrained with how much total surface area we can have, it can only be maximum 12. We want to know what is the total volume we can attain. Okay? So what we do is we want to find critical points, namely maximums and minimums, right? So what we can do is we can, over here in this equation, notice that we can solve for z. Let's bring this equation over here. I'll get 12 minus the xy is equal to 2xz plus 2zy. I'm going to pull out a 2 here. I got an xz plus a zy and divide by both sides. And that means I get z is equal to 12 minus xy divided by xz plus zy. Okay. So now that we solve for z, this z, if you will, just becomes a function purely in x and y, which is nice. Furthermore, we can now replace z in this equation to get a new volume equation, and our volume equation will be in variables x and y only. So it'll be x times y times our new z, which is 12 minus xy, divided by x plus z, xz plus zy. Okay. Here's our new v of xy. Okay. And clearly you can distribute that xy to get 12xy minus x squared y squared, everything divided by this xz plus zy, okay? So here's our v of xy. What we want to find is what is partial v partial x, and we want to set it equal to 0. We want to find partial v partial y, and we want to set it equal to 0, okay? Doing that takes a very, very long time, as you will see by doing one of them. Okay? Doing that takes a while. All right? Recall that this is our V. We'll do one of them laboriously. So, partial V, partial X is the same thing as 12xy minus x squared y squared prime times the other function xz plus zy to the negative 1 plus xz plus zy to the negative 1 primed times our 12xy plus our x squared y squared, right? So notice over here, what I get is it's with respect to x. So this is 12y minus 2xy squared over here, all times my xz plus zy to the negative 1. And then over here, we get plus a negative 1, xz plus zy to the negative 2, partial x, the inside x, z plus zy. And this comes along for the ride, 12xy plus x squared y squared. Okay, so then notice that this breaks down to 12y minus 2xy squared divided by xz plus zy minus this right here multiplied times that. This gives me a z, and that's it, right? This just gives me a z, and that's it. So this becomes z, we'll put a negative over here, minus, for this negative sign, minus z times 12xy plus x squared y squared, everything divided by this term squared, xz plus zy squared. Now to obtain a common denominator, I have to multiply top and bottom here by one of these terms here. So we'll move the calculation. We'll move the calculation up here. Okay, so I multiply top and bottom here, so I get xz plus zy times 12y minus 2xy squared, all right, minus z times our 12xy plus our x squared y squared, close it, everything over the same denominator, xz plus zy squared. All right. Notice that when we FOIL, rearrange the terms, do all of that laborious calculation, we will get it all the way down to what we get is if this is set equal to 0, we get that ends up decomposing to 12 minus x squared minus 2xy is equal to 0. Okay. If you go and do this mathematical drudgery, you will get that. It takes a long time because this was just partial v partial x. You also have to calculate, this was just partial v partial x. You also have to do partial v partial y. And these steps can take a while. They're computationally heavy, and they because they're computationally heavy, not only do they chew up time, but they cause the rates of error to increase. So once we're done, we get this equation here. And I'll omit the calculations for partial v, partial y to save time. That will take quite a bit of time. But whenever you do the similar partial derivatives and calculations, you get 12 minus 2xy minus y squared. Okay? So let us focus on these equations here. Recall what we're doing right now. We are just trying to calculate the maximum and minimum values here. All right, just like in 11.7, that's the section where we calculate maximum and minimum values. We're basically still in 11.7 way of thinking. We set the critical values equal to 0, try and calculate what the partial derivatives are, and solve for the x and y. All right, so we're still doing that. Okay, so what can we do here? We notice that if we get this equation, we get that 12 is equal to x squared plus 2xy. And the same thing for this equation, we get 12 is equal to y squared plus 2xy. Right? Noticing that 12 equals itself, meaning we can set these two equal to each other. We can cancel out the 2xy, and that means x squared is equal to y squared, which implies x is equal to y. Okay, when you take the square root of both sides. And I know what you're thinking, well, what does that mean, plus or minus? Well, we only take the plus because we don't want to have negative lengths, and we don't want to have a negative volume. Okay, that's why. So now that we know that x is equal to y, we can actually plug that in to one of these equations here. So I get, for partial v partial x, I get 12 minus x squared minus 2x squared is equal to 0. So I get 12 minus 3x squared is equal to 0. And I get 12 is equal to 3x squared. And I get x squared is equal to 4. And that implies that x is equal to 2, but technically plus or minus 2, right? Well, we take the plus 2 because we don't want negative lengths. Okay, and we don't want negative volumes. So that means x is equal to positive 2. Oh, but this showed us that x is equal to y. And if x is equal to positive 2, y is also equal to positive 2. So we know x and y. Are we done? Surely we're not, because volume, the volume maximum, which we're trying to calculate, is x times y times z. But we had an equation for z, do we not? It was up here, but it got deleted. But so you guys could rewind and find it. I need to look at my notes for what z was. But really, I could rederive it. Don't want to waste time rederiving it. I just look back at our notes, what we had for z. Z was equal to 12 minus xy all over 2y plus 2x. And we know x is equal to y, which is equal to 2, right? So then I replace any x or y with a 2. Aha! So we get that z is equal to 1. So we know that the maximum volume is 2 times 2 times 1, which is 4 units cubed. Now, you would probably think, well, that didn't take that long. Well, it actually does whenever you do all of the computations. Remember, we didn't even do all the computations for partial v partial x. And we skipped all of the computations for partial v partial y. So there was quite a bit of computations having to be done here, all right, to find our final answer. So why don't we actually come up with a new method called the Lagrange Multiplier method? Okay, that's what section 11.8 is all about. all about the Lagrange multiplier method. So here's a theory behind it. And then we'll talk about the method, and we'll apply it to this very problem, and maybe another problem, if the time allows. So here's a theory, okay? So let's say you have a function, right? Here's some function. And let's say these are your level curves to your function. Here's the level curves of your function. Okay? So notice that, well, I didn't really draw this well for it to like be apparent. Maybe I should also use different colored chalk as well. So here's our axes. I can do that. Here's our function in orange or in yellow. Okay. And let's draw the level curves in red. Okay. Notice that this level curve intersects the function at a maximum value right here. Okay. All right. So we'll say that our function we want to maximize our function f of xy, right? Just like last time we wanted to maximize this function. This v, it was a function of x and y. Remember? Let's say we want to maximize some f of xy. Okay? And we want to maximize f of xy with the constraint g of xy is equal to k. All right? So our constraint really is the red, the level curves, if you will. We want the level curve to intersect the actual value of the function at some point P. Okay? This is some point P right here. And let's say it's equal to some x naught, y naught, and z naught, right? Okay. And let's say our function is equal to f of xy is equal to some c, all right? Notice that this function g of xy is equal to k, which is in red, and this function f of xy, which is equal to c, this is in yellow. They share a common tangent line. Look at that point P. So they share a common tangent line on top of sharing a common point. That is the crux of this argument. If you recall, they share a common tangent line. That means they share a common derivative value, and that the gradient vector is going to be perpendicular to the derivative vector. Okay? So f has an extreme value at some p. So this is what we're supposing. F has an extreme value at p. P is equal to x naught, y naught, and z naught. Okay? So let's say we have some curve C. And let's say that f has an extreme value at p on the surface S, and there's a curve C going through that point P, and the curve C is parameterized by R of t is equal to some x of t, y of t, and a z of t. All right? It's a parametric vector equation. And yeah, it equals C. Parametrized vector equation. Okay? And let's assume that there exists some T naught such that this equals essentially it's like the displacement vector from the origin to the point P. Then the composition h of t is the composition of f of this value. Okay. So since f has an extreme value on c at x naught, y naught, z naught, that implies h of t naught has an extreme value. And that extreme value is equal to RC. Okay, and so this is equal to an extreme value, but it's a constant, right? So when you take the derivative of both sides, we get h prime of t naught is equal to 0, because the derivative of a constant on the right-hand side is a constant. But here's now the argument. This is where we're going to take off. We're going to take the argument, and we're going to go here. All this extra theoretical framework to create Lagrange multiplier method. Well, actually, you'll see how valuable it is when the problems become very difficult. Lagrange's method is actually more efficient in calculating maximum and minimum values given a constraint. And you'll see, so h prime of t naught equaling 0, this actually implies that the gradients of our f evaluated at x naught, y naught, z naught, the gradient vector, dot our derivative of r at evaluated at point t naught is actually equal to 0, because by definition, this is equal to h prime of t naught. Recall what the gradient really was, right? And recall what r prime of t naught really means. If this is r of t, r prime is just the derivative over here with respect to t, dx dt, dy dt, dz dt, okay? That's what's going here, dx dt, dy dt, dz dt. Over here, these are all the partials of f with respect to the variable evaluated at x naught, y naught, and z naught. Okay? So we may assert that the gradient and the gradient vector and the derivative vector are actually orthogonal. Why? Because this is the dot product over here. And that means the gradient of the vector times the magnitude of the gradient times the magnitude of the derivative cosine of theta is equal to 0. And at what theta is cosine assumed the value 0? Because we know these two are non-zero. That means cosine of theta must be 0. That implies theta must be at what angle? It must be at pi over 2, because that's when cosine of theta is equal to 0. Okay? So all of this to say that the common tangent line that the function has implies that the gradient of f is equal to some lambda of the gradient of g, where lambda is just an element of the real numbers. It's just some scalar. So now we may assert that f is perpendicular to r prime. Okay? So our gamma over here is called the Lagrange multiplier. This gamma is called the Lagrange multiplier. Because you multiply it times a function. And it tells you how to optimize given this constraint. So, to see what I'm talking about here, well, let's apply it to the problem we did before. So here's the method. Step number 1, if we want to maximize or minimize our function f of x, y, z with the constraint equation, let's say g of x, y, z is equal to k, like a level curve or a level surface, if you will. All right. What we do is we calculate gradient of f of x, y, and z, and we find out the lambda that will reproduce the gradient of g multiplied times the lambda of x, y, z. All right. Not only when we do that, we are going to find all x, y, and lambda, z and lambda, that maximize or minimize f Step 2 is once we find it, evaluate. All right, to do that, we say gradient f equal to lambda g, or gradient f is equal to lambda gradient g. This implies we want to find f of x is equal to lambda g of x. We want to find f of y is equal to lambda g of y. And we want to find f of z is equal to lambda g of z. And another equation we have is our constraint, f of x, y, z is equal to k. All right. So let's solve that problem we did earlier, now with the method of Lagrange multipliers. So again, we want to optimize the volume with the constraint equation of the surface area. Let's say it's equal to 12, which is equal to xy plus 2xz plus 2yz. All right, so what is the gradient of the volume? Lambda gradient of our constraint g. Notice that this is really our g. This is our constraint equation, the surface area equation, and this is our volume equation, an expression in terms of x, y, and z, respectively. So this decomposes to okay, along with this equation. Those are our 4 equations that we have. So what is partial v partial x? Oh, that's just yz. Lambda partial g partial x, partial g partial x. Well, that becomes y plus 2z, and that's it. Partial v partial y is just xz. And that becomes lambda times partial g partial y, which is just x plus 2z. Partial v partial z just becomes xy. This becomes partial g partial z times lambda becomes lambda times 2x plus 2y. So these are all our equations over here. So at this point, Lagrange multipliers requires you to solve a system of 4 linear equations, given 4 unknowns. The unknowns are x, y, z, and lambda, but you at least have 4 equations, don't you? So you can solve 4 equations, 4 unknowns, can't you? Yeah, so one way to do this is multiply all of this by x, multiply all of this by y, and multiply all this by z. Notice then we would get x, y, z on the left-hand side of each of these equations. And on the right-hand side, you would get, for this, you'd get lambda x times y plus 2z is the same thing as lambda y times x plus 2z is the same thing as lambda z times 2x plus 2y. So we've effectively been able to, using that clever multiplication strategy, we've been able to set all the equations equal to each other. All right, I'm going to call this equation 1, equation 2, equation 3. All right, what happens when we set equation, let's say, 1 equal to 2? All right, well, we get lambda x times y plus 2z is equal to lambda y times x plus 2z. I can cancel out lambdas, and I multiply through x, I get xy plus 2 xz is equal to yx plus 2yz. Okay, yx and xy are the same because we are in a commutative field. And so now we just get 2xz is equal to 2yz. I can cancel out the 2's and I get xz is equal to yz. I can cancel out the z's and I get x is equal to y. Recall, that is an expression we attained last time, but with a lot more calculations. We were able to do it with a lot less calculations. All right? Now, what if I set equation 2 equal to equation 3? Lambda y times the quantity x plus 2z is equal to lambda z times 2x plus 2y. Cancel out some lambdas. Distribute some yx plus 2yz here, and I get a 2zx plus 2zy over here. All right. I have a yz over here. I have a yz over here. I could cancel them by subtracting 2yz from both sides. So now I have a 2xz is equal to yx. So let us not forget that x can't be equal to 0, right? Because then we wouldn't have a volume. Because volume is equal to x, y, z. If x was equal to 0, we wouldn't have a volume. All right. So notice that we can actually cancel out an x over here. And it's okay to do that. We get y is equal to 2z. All right. But y and x are the same, so 2z is also equal to x. All right. So we get that equation, which is really good, because what can we do now? We can replace every x and every y in our constraint equation with a 2z. Guys, this is basically systems of linear equations. So really, since systems of linear equations are old news mathematically, and that they're easy to solve, compared to partial derivatives and doing it over and over again, see, this just requires one partial derivative and one variable, and solving some systems of linear equations. So I get 12 is equal to x times y plus 2x times, or what am I doing here? We want this all in one variable, okay? So we want it all in one variable, so we want to switch every x and y with a 2z. So this becomes a 2z times a 2z plus a 2 times a 2z z plus 2 times a 2z z is equal to 12. So 12 is equal to 4z squared plus 4z squared plus 4z squared, which is equal to 12. I can factor out a 4 and divide by 4. And so I get 3 is equal to z squared plus z squared plus z squared, which is 3z squared. Divide both sides by 3. I get 1 is equal to z squared. Take the square root. I get z is equal to technically plus or minus 1. But we don't want to have a negative length. So we just take positive 1. So we now know that z is equal to positive 1. And if y is equal to 2z, then that means y is equal to 2 times 1, which is 2. But then y equals x, so x is also equal to 2. So I get x is equal to y, which is equal to 2. And I get that z is equal to 1. And so then we calculate our volume maximum, which is x, y, z, evaluated at the optimal values. So I get 2 times 2 times 1, which is a 4. So we get the equivalent expression utilizing a different method. Okay. So let's try using Lagrange multipliers on another example. One more example. Let's say our function f of xy is equal to x squared plus 2y squared, and our constraint is the circle of radius 1. Okay? Let's use Lagrange multipliers to optimize what is this constraint. Notice that this is our g of xy, and this is our f of xy. Okay? So to use Lagrange multipliers, we have to calculate the gradient of f, set it equal to the lambda of the gradient of g. Okay? So what we get is f of x lambda gx. We get fy lambda gy. We get fz lambda gz. You guys understand why that's happening, right? This is a vector. Its components are partial f, partial x, which is the same thing as f of fx, fy, fz. That's equal to something that, when you distribute the lambda, is lambda gx, lambda gy, lambda gz, right? So we set each vector component equal to each other. So the first one is f of x is equal to lambda gx. That's where we're getting that stuff. So then this becomes partial x of this, which is 2x, is equal to lambda partial x of this, which is 2x. All set equal. Okay, so then this is partial y, which becomes 4y of f. This becomes partial y of g, which just becomes lambda 2y. Over here, there is no z, so this is trivial. Okay, so now I get 2x is equal to 2 lambda x. Cancel the 2 x's out. I get 1 is equal to lambda. Over here, I cancel out the y's. I get 4 is equal to lambda times 2. So I get lambda is equal to 2. So what's going on here? We got lambda equal to 1, and we got lambda equal to 2 over here. All right? What's going on? Well, one thing that I omitted was, that when you take partial g of this, you're also taking this, let's say partial y is just 2y, but that's equal to partial y of 1, which is also a 0. So this could be set equal to 0, and by the same token, that can be set equal to 0, right? So although this lambda is equal to 2 stuff is the actual route you can go, it's not the route we want to go, because solving for lambda is not what we're interested in. We want to optimize what x and y are, right? So that's why I'm retracing my steps here. We want to know what x and y are, not what lambda. So this is 4y is equal to lambda 2y is equal to 0. I just went down that path, and I didn't need to go down that path, right? Okay. So we notice that we do actually are able, so 2x is equal to 2 lambda x. I can cancel out some 2's. I get x is equal to lambda x, right? So so this does truly imply anything times another thing, giving you the identity. This implies lambda is equal to 1, which we had attained in a different way last time. We just divided by x, and we get that is equal to 1. Okay? That's when you set these two equations set equal to each other. All right? What happens if you then actually decide to put these two equations set equal to each other? So it branches off. It's a dichotomy. One dichotomy goes this way, this dichotomy goes this way. So we can say lambda times 2x is equal to 0. What does this tell us now? Well, if I divide both sides by 2x, I get lambda equal to 0. And as you saw over there, when I did something else, lambda equal to 2. So what's going on here? Well, what we find out is just in this dichotomy alone, just analyze x. Don't even think about y yet. Treat that as a separate story. Treat this as one. When we just analyze one dichotomy, this equation equal to that, what are the consequences? Lambda is equal to 1. This equation equal to that, what are the consequences? Lambda is equal to 0. Okay. We know x is non-zero, all right? But even so, if we get this and we divide it by 2, I get lambda x is equal to 0. This implies lambda is equal to 0, or x is equal to 0, and we don't want that. Okay? So x equals to 0. So let's think about this in here in this box. We're not even talking about this dichotomy yet. So that lambda is equal to 0 or x is equal to 0. Let's break that into case 1. X is equal to 0. All right? That implies when we get x squared plus y squared is equal to 1 in our constraint equation, that means y squared is equal to 1, which implies y is equal to plus or minus 1 when you take the square root of both sides. Okay, so let's take now lambda equaling 1. Case 1, lambda equals 1. Case 1, x is equal to 0, lambda is equal to 1. So if that's the case, y is equal to 0. Why is that? Well, lambda equaling 1, we now involve this dichotomy, especially this piece of the equation. Lambda times 2 times y equaling 0. If lambda is equal to 1, that means this is 2y is equal to 0, meaning y, divide both sides, I get y is equal to 0. So I'll I'll say as a consequence of this assumption, we get y is equal to plus or minus 1, or y is equal to 0. Okay? And if y is equal to 0 inside our constraint, x squared plus y squared is equal to 1, that implies that x squared is equal to 1, which implies that x is equal to plus or minus 1. Okay? So what are all of the possible values here? Notice that, again, lambda was just a tool. Really, we wanted to care about what is all the possible x and y's. Because our function f of xy is a function of f and x, of f and xy. So it's a function of just x and y. That's what it's called, f of xy. So then when we list all of the values here, what are all the possibilities we get with all the cases? So we got x is equal to 0. We got x is equal to 1. We got x is equal to negative 1. We got y is equal to 0. We got y is equal to 1. And then we got y is equal to negative 1. All a consequence of square rooting, right? So combining all of these with their following assumptions, we got 0. When x was 0, y was 1. When x was 0, y was also negative 1. When x was 1, y was 0. And when x was negative 1, y was 0. Remember? When y was 0, x was plus or minus 1. Y was 0, x was plus or minus 1. And similarly, when x was 0, y was plus or minus 1. So that's just a consequence of our calculations. As I told you before, lambda is really just a tool. Lambda can be a lot of different things. We saw lambda equaled 0. We saw lambda possibly equaled 1. We even saw lambda possibly equaled 2. But lambda was just a tool for us to find the real parameters of interest, x and y. Okay, so we get these possibilities. So our maximums and our minimums must be those possibilities. So let's evaluate the function and see whether it's a maximum or a minimum at these values. Really, we find f of 0, 1, which is equal to, what was our original f? X squared plus our original f of xy is equal to x squared plus 2y squared, right? So f of 0, 1 ends up becoming 0 squared plus 2 times 1 squared, which is 0 plus 2 times 1 squared, which is 2. Okay, so this becomes a 2. Similarly, f of 0, negative 1 outputs the same thing too. F of 1, 0 will output a 1, and f of negative 1, 0 will output a 1. We notice that these two are the highest values out of the bunch, so this is the maximum point. Meaning our function f of xy has maximums at those evaluated points that produce the maximum outputs. And by the same token, if these are the smaller ones, these indicate the minimums, meaning our function assumes minimum values at 0, negative 1, or at 1, 0, and negative 1, 0. That's where it assumes minimum values. Okay? So it might seem that, okay, they're both kind of complicated. Well, which one's better than the other? But the method of Lagrange multipliers, whenever you do many examples, you will realize that it is actually more efficient and easier to do than the standard way of setting the partial derivatives with respect to each variable is equal to 0 and solving. Sometimes that is actually really hard to do because you may not have enough equations to be able to solve them, and they're more difficult in nature.